Hello class. In the last couple of lectures, what we've been working on are the rate laws for a certain reaction. And that's related to how the rate is affected by the concentration of some of the components in the reaction and how the concentrations changing over time affects the rate. What we're going to do today is start talking about what are called the integrated rate laws, which are a set of formula that describe how a reaction rate is dependent on the concentration of the reactants and also on time. So the rate laws that we've seen thus far relate the rate of the reaction and the concentrations of the reactants. We can also determine a second form of the rate law that relates concentrations of reactants and time. This is the important part. So these are called the integrated rate laws, and we have a few sets of equations, and for a first order reaction, we have the most equations because this is generally the most common type of reaction where you have a first order reaction. So here, shown first on the left, this is the first order integrated rate law, where you have the natural log of concentration of initial A over the concentration of A at time t is equal to the rate constant K times T time. If we flip this, we can set it equal to negative KT. So if we then put the concentration of A at time T divided by the concentration of A initially, if we just flip that from the original one, we get a negative KT. If we then rearrange, we can get another form of the equation, which is a concentration of A at time T is equal to initial concentration of A times E raised to the negative KT, which can sometimes be useful. If we're looking at graphs, what is very useful to us is an expression in the form of y equals mx plus b, which is a linear line, where we have the natural log of a, which is y, is equal to negative kt, plus the natural log of a initially, which is our y-intercept b. For a second order reaction, the only form that we're going to really be considering is the linear line form, which is in the form of y equals mx plus b, where y is 1 over a, which is equal to k times t, plus 1 over the initial concentration of a. We can also take a look at a zero order reaction, which is independent of concentration. A rate law there is going to be equal to k times a raised to 0, which is just going to be equal to k. In that situation, we have a linear line expression that is a is equal to negative kt plus initial concentration of A. So we will be using these equations a lot, and then in a few pages we're going to see some notes that summarize a whole bunch of data that you will be provided. So let's look at an example. So example 7, the rate constant for a first order decomposition, so just having the first order part of this gives us a lot of information. The first order decomposition of C4H8 at 500 C is 9.2 times 10 to the negative 3 inverse seconds. How long will it take for 80% of the sample of C4H8 to decompose? The reaction is shown here. What is given to us as a first order reaction, we're also given a K rate constant, and we're solving for T. So we can use the original first order integrated rate law in order to solve this type of problem. And here's how we would solve this type of problem. If concentration of A at time 0 is equal to x, what we're really solving for is at what time is there only 20% of the sample of A remaining. So if 80% of it decomposes, we have 20% left over. So let's see how we would use that information and the integrated rate law to solve for T. So first, our initial concentration of A is going to be equal to x. At a concentration of A at time t is going to be 0.2x because 80% of it's gone. So we plug those values into our integrated rate law expression, and we get the natural log of x over 0.2x is equal to our rate, k. 9.2 times 10 to the negative 3 inverse seconds times t. X's cancel, and we get a natural log of 1 over 0.2, which is equal to 9.2 times 10 to the negative 3rd inverse seconds times t. The left side of the equation is a number, 1.609, after you solve for this, and you get that equal to 9.2 times 10 to the negative 3 inverse seconds times t. You solve for t. When you solve for t, you take 1.609 divided by 9.2 times 10 to the negative 3, and you get 1.7 times 10 squared. When you divide by this value, you're also dividing by the units. And when you take 1 divided by inverse seconds, you get seconds. And what we're left with is a time that is equal to 170 seconds, which is about 3 minutes. On the next page, we're going to take a look at an integrated rate law and our decomposition of hydrogen peroxide from an earlier example. So, our first example from kinetics was when we were monitoring how a change in time increasing by intervals of 6 hours, and we were monitoring how that affected the concentration of H2O2 over time. So, when we have our natural log of H2O2, this should be unitless at this point. If we plot this information, we can get a linear line if we plot the natural log of the hydrogen peroxide concentration over time. So if we plot this column here as the y-axis, and we plot this column here as the x-axis, we get a linear line. And that's how we can use graphical data to figure out what the rate law is. Turns out, when you have a y-axis of the natural log of concentration over x-axis of time, this must give you a first-order reaction. So what can we do with this information? Well, the equation for a linear line is y equals mx plus b. Our x-axis is t. Our y-axis is the natural log of H2O2, which means our y-intercept, b, for our linear line, is going to be the natural log of O2 at time 0. Because if we take our x-axis and we go all the way to the left, that's at time 0. So that gives us another data point. When we bring that information to the equation of a line, we get the natural log of hydrogen peroxide is equal to m times t plus the natural log of H2O2 initially. That is equal to our linear line equation from page 92 for a first-order integrated rate law. Therefore, we know that m must be equal to negative k, because we have this form for our linear line, because this is a first-order reaction. And we have our slope m is equal to negative k. So, what we are looking to do is take this data and our linear line equation and calculate k. So let's do that. So when we calculate k, our slope is going to be the change in y over change in x, which is the change in natural log of H2O2 over a change in time. We're going to use trial 3 and trial 2 arbitrarily to solve for this. So we take our trial 3 data, subtract our trial 2 data. So that our change in the natural log of H2O2 is going to be from trial 3, which is negative 1.386, and we subtract our trial 2 data, which is negative 0.693, shown here. Each interval is over 6 hours, so we take 12 hours minus 6 hours, we get 6 hours, and we get negative 0.693 divided by 6 hours is negative 0.116 inverse hours. Our slope m is equal to negative k. If we divide both sides by negative 1, we get a negative m that is equal to k. Our m slope is negative 0.116 inverse h that we just calculated. So we bring in this value for m, and then the negatives cancel, and we get a k that is equal to positive 0.116. So that is not immediately obvious to many people when we are using slopes of lines, so I wanted to take that step by step. We solved for m, we bring m in, it's multiplied by negative, and we get a positive k. What we're going to find out is that information like this is really, really useful. We can take a set of data and figure out the rate law, which is based on concentration, which we've done before. We can also take graphs, which we just did, and figure out the rate law, which is based on concentration. We can also take the rate law units, the rate constant units. If we know the rate constant, turns out we have unique units for a given order for rate constant, and we can then determine the rate law. For example, our k in this situation was inverse hours. Turns out if you have an inverse time for the units of your rate constant, you always get a first order reaction. So there are now 3 different ways that we have in order to get to the rate law, being a first, a second, a third order, or a 0 order rate law. That's dependent on concentration. Once we know the rate law, we can then use our set of integrated rate laws, which are dependent on concentration and time, and we can solve for any information that we need to. Let's now take a look at graphs for other orders. So if we continue with our integrated rate laws, here are our rate law graphs for the following situations. A zero-order rate law graph looks like this, where you have your concentration of A is plotted against time, your slope is negative k, and the equation for the linear line is concentration of A at t is equal to negative kt plus the concentration of A initially. For a first order reaction, which we just saw, the natural log of A is plotted against t to give you a linear line, which is m is equal to negative k, and the equation for the linear line is natural log of A sub t is equal to negative kt plus the natural log of A initially. Finally, if we plot a second order reaction, we get a linear line when we plot 1 over A versus t, and the slope is positive k. So we get 1 over concentration of A at t is equal to kt plus the 1 over the concentration of A initially. So if you were just given a set of data, you can plot it 3 different ways. Concentration of your component over time versus time, the natural log of your concentration versus time, and 1 over your concentration versus time. If you get a linear line for the natural log, you have a first order reaction. If you get a linear line for 1 over A, you have a second order reaction. And if you get a linear line for A over time, you get a zero order reaction. You will only get a linear line for one of these 3 scenarios, and that will tell you what the order of the reaction is. So how can we use integrated rate laws for something that's useful? Well, for that, we turn to the half-life of a reaction. So the half-life, T sub T, is the time required for half of the amount of reactant to be consumed. This is really important, especially for things like radioactivity. So we're going to return again to our decomposition of H2O2. And we're going to determine the half-life for the decomposition of hydrogen peroxide, where we have a K that's equal to 0.116 inverse hours. We know that first-order reaction gives us inverse time, so that's one way that we could determine that this is a first-order reaction. So here's that, again, set of data. By inspection, which is the scientific way of essentially saying eyeballing it, that after every 6 hours, we can see that the hydrogen peroxide concentration is actually going down by half. So by inspection, we could determine that the half-life for hydrogen peroxide decomposition is about 6 hours, because after every 6 hours, the concentration of it is going down by half. It's a really, really useful, a really useful rule of thumb for how to gauge how quickly something is decomposing. 6 hours is pretty slow. If you have a half-life of something that's radioactive in a couple of minutes to hours, it's extremely deadly. So the equation that's useful for the half-life of something is going to be equal to our integrated rate law for a first-order reaction, which is the natural log of our component A initially divided by our component A concentration at time t, which is equal to kt. If we rearrange this equation and we divide by k, we get t is equal to the natural log of initial A over divided by the concentration of A at time t times 1 over k. At a half-life at t1 half, we would get the concentration of A is equal to 1/2 of the concentration initially. So now let's plug in that information into our integrated rate law, and we get a half-life that is equal to the natural log of A initially divided by 0.5 A initially. The A initials cancel, and we get a T of 1/2 that's equal to the natural log of 2 times 1 over K, because 1 divided by 0.5 is 2. The natural log of 2 is 0.693. So a half-life equation for a first-order reaction, without including any actual data and just simplifying our equation, our T1/2 is equal to 0.693 divided by K. This is the equation for a first-order reaction. Now let's use this equation with our data. So our half-life is going to be equal to 0.693 divided by K. We have already determined that our K is equal to 0.116 inverse hours. So all we have to do is we take 0.693 divided by 0.116 and we get 5.97. Again, we're in a situation where we're taking 1 divided by inverse hours, so we get positive hours, which are our units. 5.97 is about equal to 6, which is what we eyeballed from our data. So we have a 6-hour half-life for the decomposition of hydrogen peroxide. In the next example, it's a very quick example showing a different way of presenting data. Concentration is going down by half for each one of these data points, which means that any one of these data points is going to be equal to our half-life in seconds. So our T1/2 is equal to 2.16 times 10 to the 4th seconds. To solve for k, we just take T1/2 is equal to 0.693 divided by a rate constant k. We rearrange and get that k is equal to 0.693 divided by t. 0.693 divided by 2.16 times 10 to the 4th seconds is equal to k, which is 3.21 times 10 to the negative 5th inverse seconds. Again, we see that first order reactions have units for the rate constant that are equal to inverse time. Finally, on our next page, we can summarize a bunch of rate law information. So our information for rate law is summarized in columns for 0, first, and second order, where we have rate is equal to k for 0, first order it's k times a, and second order is k times a squared, or possibly a times b, or something like that. Our units for a first order reaction are inverse seconds, or any inverse time, and we have different units for 0 and second. And here in this row, you can see integrated rate laws, you can see the plot needed for a linear best fit line, and we have the relationship between the linear line and the constant, and then finally half-life equations. We derived the T1/2 for first order, but we're just going to have provided for you the 0 and second order half-life equations. So this table you will always have provided for you. And that is the end of the material for today.